Today we're going to talk about aqueous reactions and chemical analysis. So first we'll talk about gravimetric analysis. So gravimetric is weighing something. And then we'll do a big section on titrations. Titrations are specific types of reactions in which you're trying to quantify the concentration of an unknown solution with a known solution. Within that idea of a titration, we'll have an equivalence point and indicators to indicate when the titration is complete. And as a very minor note, we'll talk about redox titrations. Most titrations that we're going to be dealing with are acid-base titrations, and we'll introduce redox titrations, though I won't expect you to know that much about them, besides the fact that titrations are not just acid-base. You can use a lot of different types of reactions within titrations. So here we can try something. We'll talk about gravimetric analysis. So again, it's this analytical technique based on the measurement of mass. So if you have a 0.8633 gram sample of an ionic compound containing some amount of chloride ions and an unknown metal cation that is dissolved in water, if you treat that with a bunch of sodium nitrate, you can cause a precipitation of that silver nitrate or silver chloride. If you measure that to be 1.5615 grams of the silver chloride, what is the percent by mass of chloride in the original compound? Okay, so this is the problem we're going to try and go through. This is using that solution stoichiometry for ions that we specifically learned about in the last section. So this is that same problem, just smaller from up top. So first and foremost, we need to remember all that chloride in this silver chloride precipitate is from that original 0.8633 gram sample. Okay, so that's the first bit of information that we need to know. So we can kind of work our way backwards from that silver chloride precipitate back to the amount of chloride in that original sample. So we have grams of silver chloride. We can then go to moles of silver chloride. We see that there's a 1-to-1 molar ratio between moles of silver chloride and moles of chloride. That was that ion solution stoichiometry. And once we have moles of chloride, we can get to grams of chloride. We're going to need to get to grams of chloride because the mass percent of chloride in the original sample, if we find however many grams of chloride there were, we can divide that by the mass of the original sample and multiply that by 100%, and that is the mass percent of chloride. So we really just need to get to the grams of chloride and then plug that in for our mass percent for chloride. And you can see here we have a nice track that we've done many times before, grams of substance A through grams of substance B. In order to do that mole-to-mole conversion, we need a balanced chemical equation or some technique of knowing what that mole ratio was. Here again, because we know something about solution stoichiometry, we can see that for every 1 mole of silver chloride, that came from 1 mole of chloride aqueous ion floating around in solution. So we'll go through this fairly quickly here, but we can take that original sample, that original precipitate, 1.5615 grams of silver chloride that has precipitated. We can use the molar mass of the silver chloride, 143.32 grams per mole, so we can convert to moles of silver chloride. Next, again, we have that 1-to-1 mole ratio that we talked about between silver chloride and our chloride ion. And then lastly, we can convert to grams of chloride using the atomic weight of chlorine. So remember that 1 extra electron isn't really changing anything. Really, this is just chlorine, the atom, right? So that 1 extra electron does not need to be accounted for in this measurement. So we can just look at the periodic table, 35.45 grams of chlorine per mole of chlorine, and that'll get us to 0.3862 grams of chloride that was precipitated out in that silver chloride. So that must be the grams of chloride in that original sample. So we can just plug that in into that bottom equation, and we can find that about 44.74% of that original 0.8633 gram sample should be associated with chloride. So 44.74% chloride by mass in that original sample. Okay, so this was using gravimetric analysis. We were just weighing out different things, but we knew something about the mole ratio and how to interconvert between masses and moles, which we've done for a long time now, and understanding what was actually occurring in that solution. All of the chloride in that original silver chloride precipitate is from that original 0.8633 gram sample. All right, so we're also going to talk here about acid-base titrations. So like I very briefly mentioned in the intro, solutions of accurately known concentrations called standard solutions, those can gradually be added to another solution of an unknown concentration while very carefully measuring the volume that has been added. And then we will have some sort of way of knowing when that chemical reaction between the two solutions is complete. We'll find out that that's going to be with an indicator. If we know the volumes of that standard solution and the unknown solution used in that particular titration reaction, and we knew the concentration of the standard solution, we can then calculate the concentration of that unknown solution. Okay, so in this we're going to need to know the balanced chemical equation. We're finding out how many moles of the thing that is being titrated were needed to react completely. Okay, so some common examples: solutions of a strong base, sodium hydroxide, can be used as a standard solution in titration. We actually first need to standardize it. Sodium hydroxide can react a little bit with carbon dioxide in the air. So if you have an old solution, you may need to standardize it. So we can standardize that by titrating it against an acid solution of accurately known concentration. Okay, this is the most common kind of style of titrations, are these acid-base titrations. So like I briefly mentioned, we can use an indicator in order to determine when the reaction is complete. So for example, phenolphthalein is a really common indicator here that you can see on the right-hand side. In acidic conditions, it is colorless, it's clear. But then once you form a base, once it becomes very slightly basic, you'll start seeing it turn pink. So because of that, that's kind of a way in which you can have an acidic solution. Once all of that is neutralized with a base, let's say, it'll then turn pink, or vice versa. The pink would go away, depending on which solution you're titrating, whether it's an acid or a base. And this is trying to indicate where the equivalence point is. The equivalence point is that stoichiometric equivalent between the acid and the base. So that is where the acid has been completely, perfectly neutralized. Recall, in an acid-base neutralization reaction, you have an acid coming together with a base to form water. So you have H+, which is aqueous, that's the acid, plus, let's say, hydroxide, OH-, which is aqueous. Those can come together to form water, which is neutral. And that is called the equivalence point. If you have exactly one equivalent of H+, for every one equivalent of OH-. Again, this is kind of that equivalence point is we're using the indicator as a proxy for that equivalence point. A lot of times you'd like for there to be something very obvious, like a very sharp change in the color of a solution, for example, but there are other types of indicators. And this one specifically is for acid-base reactions, and there's a number of different types of indicators. Phenolphthalein is just one of the more common ones because of that pink color to clear transition, which can be very obvious, as you can see on the right-hand side. So let's try one of these. Here we have a volume in milliliters, or we're trying to find the volume in milliliters of a 0.203 molar sodium hydroxide solution. What volume is needed to neutralize 25 milliliters of a 0.188 molar sulfuric acid solution? Okay, so here, we're going to write what we know. I have the volume of my sodium hydroxide is unknown. That's what we're aiming for. I have a molarity of my sodium hydroxide. I have a volume of my sulfuric acid. Recall that sulfuric acid was H2SO4, and the molarity of that sulfuric acid. So I have all of these things ready to go. So here, I think you can see we have two molarities in one volume with one volume unknown. So we can just use this M1V1 equals M2V2, right? Hopefully you were kind of concerned by that. We absolutely cannot use M1V1 equals M2V2. Remember, that was just for dilutions. So here we're actually performing a chemical reaction. We can't assume that the number of moles of the first solution are equivalent to the number of moles of the second solution. That was what was needed in order to use this particular equation, which was true for all dilutions. Here, you could have not a 1-to-1 mole ratio between your two reactants. This is a chemical reaction. So, in fact, here we definitely do need to take a look at our balanced chemical equation, make sure that that we get this solution stoichiometry correct here, and we can do this with just classic dimensional analysis. So, with dimensional analysis, there's a few things that'll be needed. One of them is, remember, let's write our molarity not in terms of just with that capital M or with the capital M with the underline under it like I do. Let's write that out in the actual units that we know will be useful. So for 0.203 molar sodium hydroxide, that's 0.203 moles of sodium hydroxide per liter of sodium hydroxide solution. Same thing is true for sulfuric acid. We can convert that. All right, now we also need to get a balanced chemical equation. I trust that we're able to do this at this point, so I'm not going to spend too much time with that. But this is an acid-base neutralization reaction. So we have sodium hydroxide coming together with sulfuric acid to form water and some sort of salt, in this case sodium sulfate. And in order to balance that, we're going to need two equivalents of sodium hydroxide for one equivalent of sulfuric acid to form two equivalents of water and one equivalent of sodium sulfate. Okay, so I think we can see now that it's going to take 2 moles of sodium hydroxide to neutralize 1 mole of sulfuric acid. That's because this sulfuric acid is a diprotic acid. Okay, so we're aiming for milliliters of sodium hydroxide. That was what was asked for in the question. Now we kind of have our knowns, we have our balanced chemical equation, so I think we can start moving forward. Again, where we're going to want to start is the thing that we know the most about. We know quite a bit about the sulfuric acid solution. We know both the volume and the molarity. Using volume and molarity, we can get to the number of moles of sulfuric acid. And we need to get to moles in order to interconvert between moles of substance A and moles of substance B in a balanced chemical equation. In this particular case, we need to interconvert between moles of our sulfuric acid, which we can solve for first, and then convert to moles of our sodium hydroxide. We need to get to moles of sodium hydroxide because my final answer, what I'm being asked about, is something to do with sodium hydroxide. I'm asked for the volume of sodium hydroxide. We'll be able to use the molarity of sodium hydroxide, which is presented in the question, along with the moles of sodium hydroxide, which we can solve for, to get to the volume of sodium hydroxide. So that's the general path here. So we've seen this sort of setup before, but we have 25 milliliters of sodium, or of sulfuric acid. Again, start with the simpler of the two. So here we can we'll need to interconvert between milliliters and liters, but we'll get our volumes to cancel with a portion of our molarity to leave us with moles. Okay, so if we were to stop right here, we would be in moles of sulfuric acid. Now we can use our 2-to-1 ratio. We can say for every 1 mole of sulfuric acid, I will react with 2 moles of sodium hydroxide from our balanced chemical equation. Okay, so now we're in terms of sodium hydroxide, and now we only have one other bit of information that we have not used, and that's the molarity of sodium hydroxide. And we can use that molarity to interconvert between moles of sodium hydroxide, which is what we currently have, and liters of sodium hydroxide, which is a volume. And you can see we're looking for a volume. So then, of course, we can just do one more little change in terms of interconverting between liters and milliliters to get us that final answer, 46.3 milliliters. Now this little part right here was really important, this 2-to-1 ratio. If you did not do this, if you would have tried some other techniques without looking at that mole ratio, you probably got half of the number of milliliters here. That's a really common result, especially when this seems like you can just use M1V1 equals M2V2. That is not true. And in fact, we should not use that for anything but dilutions, certainly not using that for any sort of chemical reaction. On occasion, it will give you the right answer if that ratio is 1-to-1. But that was not the case here. And in fact, I'm going to give you very few scenarios in which it's 1-to-1 for that reason. It's a pet peeve of mine when we misuse M1V1 equals M2V2. So here we can try another one. We have a 0.1216 gram sample of a monoprotic acid that is dissolved in 25 milliliters of water. The resulting solution is titrated with 0.1104 molar sodium hydroxide solution. A 12.5 milliliter volume of the base is required to neutralize the acid. Calculate the molar mass of the acid. Okay, so we have a molarity for sodium hydroxide. We have the volume of sodium hydroxide that is used. We also have the grams of the monoprotic acid. So monoprotic acid means that it'll take one equivalent of that acid to neutralize one equivalent of the sodium hydroxide. Okay, and we're trying to calculate the molar mass. So we can kind of start there. The molar mass of that acid is going to be the mass of the acid per mole of the acid. It's monoprotic, so I'm saying per mole of H+. So we really just need to solve for how many moles of H+ were reacted in this situation. Okay. Again, our molar mass is in grams per mole, so that's how we knew we could take the grams of that monoprotic acid divided by the moles of that acid. It's monoprotic, so that's going to be the same as the moles of H+. Even though we don't know what the counter anion is for that acid, it doesn't really matter here. The solution stoichiometry still is the same, right? For every 1 mole of H+, there will be 1 mole of the monoprotic acid. Okay. So we're really aiming for moles of H+ here in our solution stoichiometry, in our dimensional analysis technique. Okay. Again, we're going to start with sodium hydroxide. That's what we know the most about. We have both the volume of sodium hydroxide and the molarity. So again, we'll take the volume times the molarity. We have to do a little bit of change here in the middle, just because we were in milliliters. We need to convert that to liters. So now we have moles of sodium hydroxide. And now, for every one, we know it since it's monoprotic, for every 1 mole of sodium hydroxide, there's 1 mole of H+, right? You can say H+ plus sodium hydroxide forms water plus the sodium ion. That would be that balanced chemical equation. But a monoprotic acid with sodium hydroxide is 1-to-1. Okay, so we would get 0.00138 moles of the H+. So we can just plug that into our molar mass equation in the sense that we just need the grams of the acid per mole of the acid. So you plug that in and we should get 88.1 grams per mole should be that molar mass of the acid. Lastly, I'm going to briefly talk about redox titrations. So this is the same idea as the acid-base titration. We want a reaction to go to completion. In this case, it's a redox reaction instead of an acid-base reaction. Again, it can be used to quantify the amount of something that's in a solution. So here we have a burette. This is the way to accurately measure the volume of our standard solution being added. So here it's KMnO4, it's potassium permanganate. Permanganate is a polyatomic ion that we should be somewhat familiar with. So that can be aqueous. You can see here it can react, it can undergo this reaction. And in the very tail end, it actually ends up becoming both the oxidizing agent and the indicator. This ends up being a colored solution. You can see that we get some sort of colored solution there. So anyway, the only real thing you need to get out of this, we're not going to ever do one of these in class, but it's just know that titration technique is more common than simply acid-base reactions. We use it a lot for acid-base reactions, but there's lots of different redox, or lots of different titration techniques using redox chemistry or various other sorts of reactions. And that's really it for the end of this chapter. We're not going to do any practice problems associated with these redox titrations.